It's very important. A lot of amateur astronomers are here who are interested in this topic just because of fun, and they like it. So I suppose it's a very strong motivation in the background. So first, take a look, what do we have? We have existing facilities, existing background, meteorites. The members of this talk have optical, infrared, X-ray, Raman laser, and various other spectroscopes. So we have a relatively nice laboratory background to analyze meteorites. We have a range of meteorite samples, not a huge, but a lot, and range of mineral references. So we can work with meteorites, and we are currently working on it, but without the meteor domain. This analysis in the laboratory could provide, for example, elemental composition, but could be linked to elemental ratio from the spectral observation of meteor trails. We can identify spectral heterogeneity, which can be linked to light curve. We are doing laser ablation tests, which can be linked to the ratio of released elements, just like during the flight in a meteorite in the atmosphere. Some further examples about laboratory facilities. These are from Czechia, Martin Ferrus laboratories, where they are working to analyze and understand how do the meteoritic bodies in the atmosphere release the elements under plasma experiments, and what are they releasing, and how can it be observed, and what the ratio means of different minerals, different observations, which are not equivalent to ratio of minerals, but ratio of observability of different ionized elements. And they also have a lot of observational facility of spectra and track optically. In Hungary we have the same. You can see the stations, some new elements which were established recently. So actually everybody knows there is a lot of facility existing in the background for meteor observation, for flight track and light analysis, for spectral observation during flight, a little bit less, but existing, and meteorite analysis in the laboratory. It would be very useful to make closer links between these different but very closely related topics. So, some suggestion from us: use the existing information on meteorite composition. We have a lot. Support the information exchange between the participants. We could build up cloud database on the internet, where, for example, one member can upload compositional data of meteorites, another person could upload compositional data of meteor spectra, and we can link these together and try to find out how can real and strong links establish between these. There are softwares mainly from Martin Ferrus also, which can be used by other possible interested peoples, but as we have heard, there's a lot of softwares in this domain, so mainly the problem might be to make them compatible regarding the use of the same results. So we can do some research on the dynamics of meteors, correlate the composition and orbits using statistics, just like among other people has already been done this, but we can also do it in this group and try to cooperate with related topics. Actually, these things, when we simply talking about, for example, atoms or light curve analysis, or what does brightness mean? Actually, these all can be linked together and somehow fused into the evolution of the solar system, origins of life and astrochemistry. These are very popular and large words, but actually the link exists in theory, but we just need to identify. Some example selected topics, how to guide this collaboration. So it is not enough that we have a good idea, link together meteors and meteorites, of course, but how can it be done? We need some guideline which help to do some real activity and produce some specific result which can be published. Here are some examples. correlate observed fireball element ratios with meteorites regarding, for example, the main elements, iron, manganese, and sodium, or specific elements. Or there are some observations or background theoretical ideas. For example, iron meteorites are stronger and they have higher ratio iron sodium ratio than stony meteorites. Could this be connected to ablation of observed properties of the flight? Or more fragile stony meteorites might ablate higher. Maybe they have different spectra if we connect the height based on optical observation to the spectra. Light curve terminal peak usually, or in theory, should point to harder meteorites, maybe to iron meteorites, which more iron or more obvious iron appearance in the spectra. We can analyze, for example, the fusion cast of meteorites in laboratory and take a look what kind of elements are missing from them, because it was the surface which was in contact with the atmosphere during the flight and released a lot of elements. If we can identify which kind of elements are missing and these elements dominate the spectra, this might be a possible interesting link, only to show, okay, where should we go on in the future. Or search for heterogeneity, or analyze the scale of heterogeneity in the meteorite samples. It might be connected to number of fragmentation events or fragmentation points. A little bit, you probably understand it's a little bit more in the background, that is not so simple like this, but you understand what do we mean. So all these are not more than ideas, but could be confirmed or rejected by joint activity. So we need to put together meteorites and meteors to find out how can we continue or what shall we do. So what do we suggest? We are starting now a collaboration, let me say just for fun, so without money or without every background establishment, between Hungary, Czechia, Greece, and probably Russia. So we are focusing on meteor spectra, meteorite composition, and fireball light curves. So actually the work is now on identify the possible links. So the way how we approach to connect these different topics. We know there is a lot of type of connection, or several has been already published, but currently I suppose the main topic is, okay, work on how to identify, confirm, or fine-tune these connections. So it's only a community action, nothing more, but potential for larger collaboration exists with everybody who is interested. Of course, then it should be good to start to think about, okay, how can we get further funding from this kind of activity. So here, as a small group, the authors searching for collaborators, and we are open to involve already existing projects and networks. So we are not aiming to produce some concurrent ideas or projects or groups. We are just thinking about it's maybe time and interesting to link these topics together, which already probably in the mind of other persons. So as a take-home message, I would like to suggest, and not take-home, but use it here. So please contact us at the meeting, Martin or Christian or Antal or me or Jakub or anybody else of these groups. So actually the main point of my talk, we are interested in your views, your ideas, and possible collaboration, because this idea is nice, but it should be developed further to make more specific scientific output and get on something really. Yes, and thank you for your attention.
Questions for Akos?
Everybody's afraid of. So actually what I wanted to say, we are open to anybody, and we are not aiming to lead such collaboration. We are only to start and initiate a new core in this activity.
Speak to the speaker again. Next up, we've got Ellie, who's going to talk about the Desert Fireball Network and how to calculate observe fireballs, calculate orbits, and find meteorites.
Can you not hear me from here? So, as Hayden introduced me, I'm Ellie. I'm from the Desert Fireball Network in Australia. And I'm going to talk to you a little bit about our data pipeline and how we automate getting orbits and finding our meteorites. So, most of you probably know who we are. We've got about 52 cameras across Australia, covering almost 3 million square kilometres of the skies in Australia. And we're expanding that across the world as well. So Hadrian's going to talk tomorrow a little bit about how our technology's improved and the hardware that we're using. So this is our data pipeline. I'm just going to shout. Can you guys all hear me?
Yeah.
Okay, this is much less frustrating. All right, so this is our data pipeline. We, when we get fireballs, we do pretty much everything up the top end for everything. So we can get a nice trajectory analysis for everything, and if we think there's a rock on the ground, we carry on and go a little bit further and do wind modelling and dark flight analysis, and eventually go out and see if we can find the rock. So for our event detection, when we observe fireballs, we basically get about 50 to 60 terabytes a week of data. And so we really need to rely on automated methods of figuring out if there's fireballs in our images. And we're moving towards neural network algorithms that try and detect fireballs in our images. So we train the data to try and figure out the difference between stars versus airplanes versus fireballs and cloud edges as well. And it works pretty nicely. We then have multiple layers of that where it sends data back to a central server and it tries to figure out if there's a multi-station corroboration for that event. If it's too low, it's also detected then there's a plane. If it's too high, it drops out the satellites. And anything really nice sends us back a little snapshot to Perth. So about 80% of our cameras have 3G connections, so we get that nice little snapshot on our computers in the morning. So we managed to get absolute timing by we use an LC shutter through at the back of our lens. So rather than getting a nice clean fireball streak, we get a dashed image. But we don't do it in a regular interval like this. We actually do it according to a De Bruijn sequence. Now this is a non-repeating sequence during the 30-second exposure. So we actually get absolute timing for every single point along that fireball trajectory that we can pick. We're actually moving away from the dot dash encoding and doing just dots, which is still usable. So this De Bruijn sequence is kind of the way that we can get absolute timing of our images without any external hardware. So it's all just in that, it's all encoded in that one image, which is really nice. So here's an example of what that actually looks like for the fireball. This is the start, and we've kind of got a 9-element sequence. If you can pick 9 dashes and dots in our old ones, or a bunch of dots in our new one, we can figure out exactly when to 0.4 milliseconds when every single point in that trail is. We can then calibrate those. Hayden does a really nice job of this, which hopefully in maybe a year's time when his PhD comes out, we will be able to share around as well. So then we can do triangulation. We can do rough straight line triangulation to get a rough approximation of height along the trajectory. We can then chop that into smaller segments and get a really nice gradient just for the top of the trajectory. And now I'm going to try and use this example as much as possible. This is a meteorite that fell on Halloween in 2016, and it fell just north of Perth. So, big thing for going back and we're now looking into getting orbits, is we can get that really nice gradient by triangulating just the upper section of the trajectory before there's deceleration or too much atmospheric influence. But as we heard kind of from Dennis earlier, trying to get that initial velocity can be quite difficult as well. So we've been really pushing hard at characterizing the errors and uncertainties that we have, not only in the observations that we get, but the model that we're using. So we're just using a simple single body decelerating single body atmospheric deceleration, and we've also got on here a Jackier fit as well, which is just a mathematical fit. That's not really going to give us as good uncertainties. Now, when we're trying to go back propagate and get where the orbits and where these objects come from back in time and propagate that, there's some really nice stuff done by Granvik that shows we don't necessarily need to have the most tiniest errors possible, but we need to know exactly, or we need to have a really good characterization of what they are at the top of the atmosphere so we can roll that back. And so we're actually using an extended Kalman filter and smoother, which does a really nice job. We actually, rather than starting our models at time 0, we actually start them at the end, because we have a much better understanding of what the final mass is than what the initial mass is. So we can kind of say, well, meteors are late, so we can probably say they're less than 10 kilos at the end. Whereas at the beginning, you haven't really got a clue. So we start them at this end, run them backwards, get a really nice initial velocity, and then run them forwards again and get a really nice final velocity. Then with those well-characterized uncertainties, we can do Monte Carlo modeling on our orbits and get a really nice orbit with that we're confident with. So another interesting thing about what we can do with our data is that, like I said, we can get the absolute timing for all of those dashes in our image, and all of our LC shutters across all of our parameters across all the network are synchronized using GPS, PPS timing to, as I said, 0.4 milliseconds. So all of our observations are synchronized, which means we can actually, rather than doing a full fit of our trajectory all at once, we can triangulate individual time steps, which is really cool. So this is obviously, with 2 cameras, it's not going to be all that great. You're going to get almost a point. But the more cameras you get, the better idea you have of where that fireball is at any given point in time. We've been using this to try and get an idea of how straight fireball trajectories actually are, and we're getting some really cool stuff out of that, which I'm going to be talking about at EPSC if anyone's going. I have some extra slides if we have time, but doesn't look like they go. It's not just gravity that acts on them towards the end as well. Atmosphere does seem to have quite a bit of an influence. So we don't want to use the extended Kalman smoother for everything, because that's based on straight line triangulation of triangulated positions. So I've been looking into particle filtering, which uses the raw observations at each time step to try and figure out mass, density, position, and all of that. So this is kind of an idea of what we've come out with. I don't know how well you can really see, but there's blue points along here. The points on the straight line trajectory from each camera observation. We've got green points on here are the individually triangulated points, those discretely triangulated points for all the time steps. These last 4 time steps only had 1 camera observation. So we can still use the particle filter on that, but as you can see, they're starting to spread out towards the line. If you then had another observation further down here that has multi-camera observations, that would collapse back to a point. But it's a really nice way of looking at our positions and modeling our fireball trajectory from just the raw data. And this is the kind of thing we can kind of come out with. We get a nice statistical distribution of final mass and density. This is for that Dingle Bell meteorite. And the red cross there is actually what the recovered meteorite came out as. So there is a possibility of high masses, but you can, again, we've got a nice statistical distribution of that. So we determined there was a rock to go look for, and we had to do some wind modelling. And it's a lot harder than you think, especially in Australia where there's not as much weather data. We don't have the nice Doppler radar that some of you guys are lucky enough to have. It's coming to WA, and we're working with the Bureau of Meteorology to try and get our hands on raw data, which currently they just throw out. So for this event, there was some there were strong winds, and it was quite varied between different wind models that we had. So we actually plotted 3 traditional fall lines for each of the wind models. That was quite a fair distance apart. It depended on the, how much information or balloon flight information we had and the length that we modelled over. We actually also have a dark flight that comes straight from the particle filter and models everything through all the different flow regimes. We're trying to use the shape that the particle filter comes out with as well. And also includes that last little bit of ablation that we don't see on our cameras because we're only sensitive to about magnitude 0. So you can kind of see the background scatter of where we thought it might be. They traipsed through this field, and on day 5 found our meteorite, which was pretty cool. And as you can see, it is a really funky shape. So what we want to try and look into is how much this shape influences not only bright flight, but especially the dark flight trajectories, because the flow regimes and drag on those different shapes can act in very different ways. So that's kind of all that I've got to talk about on our data reduction. I wanted to quickly show you just some cool stuff, seeing as this has been mentioned a few times so far in the last, well, this morning and yesterday, is the US government sensor data. Hadrian here did a really interesting analysis of trying to compare orbits and a bunch of stuff from what we get from US government sensors versus mostly ground-based observations. And this is quite interesting. These are 2 meteorite fireballs that we saw from the Desert Fireball Network. One here is almost the same as what the US government sensors came out with. But this one here, Calibiti, this is what we came out with. This is what the US government sensors came out with. And this is the little box that's shown on the right-hand side. So this is almost to Uranus. So we dug a little bit further and compared quite a few different large-scale events. I don't know if you can really see that. Basically, the summary is for size frequency studies, it's pretty good. Also good for size and strength, but it really shouldn't rely on it if you're wanting to use it for meteorite recovery. And over half the cases, the orbits didn't match. So be careful when using that kind of data. I titled this, or said in the abstract of this talk, that I was going to talk to you about the most recent fall of the Desert Fireball Network. Kind of had my backup plan of talking about Dingle Dell. But we found this guy. This is also, I guess, not really warning, but something to think about. This fell, well, we had a fireball just over 2 years ago now in South Australia, and we went searching for it earlier this year. This is what the ground looks like. There was no other rocks. I think in 5 days that they searched, they found 2 rocks total. Both of them were white, and this one. So statistically, we thought, wow, fantastic. It was, what, within about 100 meters? Less than 100 meters from where the fall line that we predicted. But so far, all the tests we've run on it say that it is not a fresh rock. So we've still got our fingers crossed. We're still doing tests on it, and we're hoping that it is the one that we're looking for. Yeah, we're hopefully maybe next IMC we can tell you that it is. And another thing, I don't know if you guys have had the chat to Stuart. He's around somewhere. He's got an awesome poster on a new low-cost radiometer that he's working on. So, do you have any questions?
Questions for Ellie? I just want to add something about the meteorite. It is a meteorite.
Oh yeah, it is a meteorite.
It's not random black rock.
Yes, Jay.
So is your pipeline going to be
We very much hope so, yes. It's working, it's getting there when we're happy that it's giving consistent, not consistent results, but once we're happy with how it's working, and we start publishing data. We'll start publishing source code on GitHub as well. The 3D particle filter paper is coming out soon, and that will be available on GitHub once it's published.
Right, Sam Bailey again. Last talk in this session, we're going to have Yang talk about the appearances of meteorite streams.
The title is The Appearance of the Meteorite Stream. It's a okay, of course. It's a non-complete work, so we give the simple title. It's a co-work. The co-work, and then my student he finished. He helped me. He helped to count, do something about count. Okay, also. Okay, one question is meteorite is in natural event. Or because he has inflation on the human. Have inflation on the human. Okay, this work. Sorry about that. Okay. So along the and okay. This work is on the meteorite cataloging grading report based on the Chinese history book 宋史明史宋史原始明史 is based in 16 to the 1644. It's about 700 years the record. Okay, so we compare our result with the meteor and the fireball. I use the Sonata database on Japan to count the material and for the material, and they use the NASA data for the fireball. And why I not choose the EDMOND, because the number, the mode is increased, so not the same. So I'm afraid the result will be not corrected because the data is the amount is increasing. So when I compare with each other, something will be not okay. Okay, so I choose these two databases. Its amount is very the same. Okay. So we compare this. It's very close. And this black line is we count the meteor number, and the red point is the fireball event. We choose 6 years data. It is six data about 100 meteor event, and in this year is 9 years. So in 9 years have 300 more 400 fireball event. It not have correlation, so it's different. So we continue our counting. Some research about the meteor shower, so we know have the meteor shower, meteor stream, and we use this. We counted this the green line is EDMOD data, and this blue line is SONOTAP data, but this pink this color is used this Japan data to use moving average, so we can have a string in here, and a string here, and it's a fireball string research, and many we find have many peaks. This line is average, and 1 sigma. Red line is 1 sigma, and the green line is 2 sigma. So they are very strong string here. This four is green meteor shower. So this peak, the Highland average is correlated to the meteor shower. And there are many, for fireball have many short peak. This the record come from the storybook, and we count by year. About in this year, very more event, but before then, 14 is very few. But we count in the this is our one. So this 1 year bin, 1 year bin. So now we don't find some maybe have, but I don't serious to check this, because we do one day bin and get a result, and we also use the moving average. So we find two important peak, because this average and 1 sigma and 2 sigma. So I point out the two peak reach the 2 sigma is here and here. So but we in about from here in about 700 years, it's all have the 52 event, only 52 event. So I think in the record, in the history record, it's maybe for the more big meteorite, because in the this history book come from the government document. So in Chinese, they don't care the small meteorite. So he care the bigger meteorite. So our result before the speaker, we have the same peak here and here, but in the November, we don't find any peak or more event. I think it depends about the size of the meteorite, maybe. Okay, so and we know the meteorite is iron or stone, so it's very high density. So we have two conclusions about for the meteorite we have mean peak here in the red array, and another important thing is I have a wide window. Sorry. Let me in this here have a wide window. It's a few event for meteor. So in physical, in the physical idea, this have a high density meteor rock in the sky, in the solar system, like this, and all the data of the meteor event is on the north hemisphere. North. So if something like this, it will scatter small meteor rock. So have the window, make the window, because the meteorite stream will clean the meteor. It's my idea now, but not. I think it's need to make sure, but it's a suggestion. It's my hope.
Any questions? Right. This concludes this session. Let's thank our speaker and all of our speakers in general.
Okay, we're continuing straight on with the next session, which is miscellaneous, which is workshops, balloons, and miscellaneous. And the first, well, okay, as you know, there have been two workshops in Hessenhoff immediately before the IMC, and so first Sis will tell us about the visual workshop.
Thank you, David. I hope I showed hard enough. If not, we have to show it back. So, indeed, there was a visual workshop. It was actually 2 half days. The PM part of August 29 and the AM part, no, full part actually, of August 30. So 1.5 days. So let me show you first why did we organize the visual workshop? Well, the new visual meter database was launched just 2 years ago. So that's a good incentive to do something with it, with EMDB. And also Christina, she developed MetFNS, which is a really easy to use package. One of the shapes is an application online where you can analyze visual meter data. And so of course it's a good idea to use this. That's also one of the incentives. Now the goals of the workshop, on the one hand we want more persons to be able and willing of course and eager to analyze visual observations. On the other hand, we want optimal knowledge and use of both the VMDB and MetFNS. So we had the idea to bring people together to achieve this. How did we choose to do that? Well, a hands-on analysis of the PERSEIDS 2018 as a joint effort of all participants. First, we thought we would look at the PERSEIDS 2016 because there was peak and extra peak. But we said, why not do something more recent? And we just embarked on this, and it was a lot of fun. We had great expectations because there were 22 participants for this workshop, and when the workshop started, actually we had 5. So my first reaction was, oh no, what happens? But in the end, there were 5 very devoted persons, so I'm not at all that. I was rather happy to have these 5 persons there. There was also one remote contributor, so Vincent couldn't make it, but he well, we made 2 videos of presentations, which we then played and laughed with and had fun. One of them was about recent enhancement of the online visual form. So it's the form on the IMO webpage where you can enter visual observation. So there has been, there have been some small changes and one bigger change on that. The biggest one is that it's now also possible to prepare a kind of CSV file. You can use an Excel, for instance, and then to upload that. And this is the main bulk of your observations. If you use the form that was there before, it's still there. You do this in several steps. It's an alternative way. It's mainly meant for people with either a lot of meters in their observation or a bad internet connection, and also for people who know what they're doing. But of course, if you enter a whole CSV file, it's more error-prone. It's more error-prone than when you have just well, with step-by-step as before. Another talk that Vincent gave is about the live ZHR on the IMO website. Perhaps you know about this. So on the IMO website, for all major showers, we have live ZHR. So this is an example. It's generated automatically from the data that are in the VMDB, and the parameters we use, the bin sizes, etc., are well optimized in some way, but it's just a fixed thing. So you cannot rely on this as real science. It's just a preliminary thing, but it is there and it's nice to use. Then what is MetFNS? It's a software to analyze visual observations. It's really nice to use. You don't have to know much, well, you have to know about visual observations, but it's easy to choose a date and a shower, a begin and end date. You choose a minimum and maximum bin size of your interval, select the minimum number of meters and other things. You fill in some more things, and then you get tables of all the exact intervals that are generated. You get plots of both R, the population index, or the ZHR. So it's really very nice to use. Playing with the data, that's what we have been doing during the burst since 2018, as you can see. It was a nice game. What we did was, well, the shower analysis routines in MetFNS. First we had a look at it. It was very intuitive to play with that. We spent a lot of time optimizing bin size algorithms. We looked at several parts in the burst return of 2018 and found which kind of bin size and other parameters best represented the data. We investigated the effect of poor versus good observing condition at some point for some of the intervals. There was too much scatter, and when we then threw away the observations that are of a limiting magnitude less than 5.5, we got better results. If not needed, we don't do this because, of course, when you throw away data, your temporal resolution can be smaller, worse. Which results did we get? Well, we derived an R population index plot here, where you immediately see there's where you see there's a dip here of about 1.7, 1.8, and also a ZHR profile, where you see this really coincides. So this real peak of the burst rate with ZHR a bit above 120 is really corresponding to this lower population index, which is of course good news. Okay, so we then also compared it shortly to radio data. So we have this, the only radio data we found in a way of which we could compare to is this radio ZHR by Shogimoto. It's an online thing, and you see that typically the big peak here coincides very well. But mainly we also zoomed in on the peak, and if you then look at, again, the population index there and the ZHR, you see that these peaks, they really correspond neatly to the filament predicted by Peter Jenniskens at, well, almost exactly. So where the arrow is where the filament has been predicted. So it's rather towards the end of the structure we see here, but for the rest it's spot on, so that was a nice find. What's the workshop outcome? Well, we will write 2 papers, WGN paper with results on this analysis, and an IMC proceedings paper to describe the different steps we made, because it took us a day or so to really find the optimal bin size, etc., to check whether if you change the bin size, the structure doesn't only change, because then you are looking at artifacts. using this MetFNS. And the publication rate in this is 2 divided by a half. It's 0.4 papers per day per person, so I challenged the spectroscopic workshop to see what rate. Thank you.
Okay, any questions? Anyone? Do you foresee the volume of visual data keeping up in this age of video?
Personally, I think so, because a lot of people keep on doing it, and a lot of new people do it. It's still relevant because you can have several advantages. Long longevity is one of them, but also sometimes you just miss events, like video systems. Okay, the coverage is getting better and better, but it's an alternative way, and what people really do is difficult to say. But it's also true that a lot of video observers also observe visually nowadays. So difficult to tell, but I think and hope it will just try from year to time.
Yeah, very good.
Just one short remark. I mean, it seems like we have finished the analysis already. For those of you who have perhaps still something on your desk at home, please do the input over the next, say, 1.5 weeks or so. We have all the parameters stored, so we rerun the analysis, including as much as we have then available. So it can be that your data will be included in the complete analysis.
Okay, thank you, Sis. The next speakers will be Regina Radavska and Juraj Toft telling us about the spectroscopic workshop.
First of all, I'm not planning to beat the other team of the workshop. We also had a big number of members, but our conclusions are still open because, oh, sorry. He was one of the organizers of the workshop, so I think that... okay, never mind. The point is that our team during the workshop counted 11 people. We hoped to have a little bit more, especially some of the key members of our community that are more experienced in some of the parts of the meteor spectroscopy. Therefore, our conclusions might not be fulfilling for everybody, but at least it's the first meteor spectroscopical workshop that gives also opportunity to some of you who are interested in meteor spectroscopy see where we are at the moment, and we gave some suggestions with the choice of the equipment and some other data reduction steps that might be interesting for you. Of course, we are planning to end up our work with guidelines, maybe not full ones at this moment. As I mentioned, we still have some not finished discussions going on. But yeah, I think that for the next IMC, it's a nice starting point. And with time, we might end up with something more stable like that after many of these orbit determination workshops that we had it in the past and still going on some more works. Yep. Thank you. So the main reason for the workshop was, of course, that some of us already are doing some meteor spectroscopy, and it's more people in trying to do something with this data, but there are always some questions that were not solved. We try to discover some of the parts as far as our knowledge allows. But at some point we need to get to the main point, so we wanted to discuss meteor spectroscopic methodology and data format that in the next steps of I think of our community is to share the data till some limits, but at least to have opportunity to also work with the spectrum from other good examples that later on can test our own and validate our own systems. And of course, as I also mentioned, provide guidance for our community. we started with pointing that there is actually some hints how to do the meteor spectroscopy so far. There is a part of the IMO photographic handbook, which nowadays through this new webpage, I personally had a problem to find it. Maybe it's something links that needs to be updated and so on. But nevertheless, I already pointed here the whole address. You can use it. It's directed to that chapter. But it was written quite long time ago, and it really needed to have an update. So we are talking about photographic observations. We are talking about using PRISM. There's a little bit also some of the examples how to reduce the data, but we need something now modern, because nowadays it's less and less of this equipment among us. So I first direct you to this document as a nice starting point, and update it with some of the keywords that we have it here. So one of the first points that we were discussing were observations per se, and it led us to present, at least those who participated, what our networks, our system already have. Of course, there is a huge range of the cameras that we can use, huge range of the groups and filters that we can use. But when you are choosing camera, try to go for the 8 bits and higher. And the same concerning the grating. The cheapest way might be the plastic holographic grating, but we need to take into account that it's going to be with the lower sensitivity. And with the groups, also the choice between 500 and 1000 might be enough for your starting microscopic system. If you're deciding to choose filters instead of grating, take into account that if the range that you are interested in is infrared, then look for the filtering that has order blocking feature. After having a lot of spectral observations, when we start to do the reduction, we need to have also information about our system and its sensitivity. And for this purpose, we can use stars, or also, as mentioned earlier in one of the presentations, we can use Jupiter to calibrate our system. But if somebody has access to the laboratory or any lamps that would be of a proper quality, then please also take this opportunity to calibrate your system in such a way for the further usage. We heard yesterday, but also today, that quite crucial for testing is test the linearity response. That also it's influencing results. And in the further reduction, if possible, keep the raw uncompressed data as it's the best quality from where we can start our work. The next step of our discussions was concerning the data reduction itself. Most of us in our teams try to apply the most common methods concerning the flats and dark movement. Instead of just a single image of flat or dark, we using a set actually of images taking the similar conditions, and then using, for example, the median, create what we call the master flat or master dark. Additionally, we also create a local background, which is just frames, additional frames that each of our cameras usually are taking before or after the event. So we are sure that in those frames we don't have a meteor. It's just pure signal at this moment. To create this basic set of files, we can use our own scripts that some of the teams already have. We can also use existing programs like ImageJ, for example, which in case of, for example, ImageJ, there is already a plug that also have astronomical application. So you can also decide if you want to have bias or pure dark only. So there is a little bit more advanced plugs that this tool have that might be helpful for your usage. Thank you. Okay. One. Of course, our images are producing images in the reference frame, which is X and Y, and then we want to actually read the wavelengths from our results. So for this, we can use, again, some lamps, or we can use already our result that we read in, and having a little bit more experience, we already identify visually which lines we see there. So we can use them, and then tangled with a polynomial fitting, transfer our pixels into wavelengths. But we need to take also into account that because of the trajectory of the flight, we not always have properly rotated our grating. Our spectra will not be perfectly perpendicular to the rows when we read the signal. We need to take, of course, into account also the tilting. So don't forget to adjust your software or your method of the reading in signal for this purpose. And the classic corrections that also should be taken into account, which is the radiometric, geometric, and also atmospheric extinction that shouldn't be forgotten. With the format, yes, so of course there was a small, longer discussion with this because some of us already are a bit used to our own system of formats and we don't want to have any other new ones. So for this, we suggest that observer is keeping its data in his own format. But for the moment when you want to share your data with somebody else or you are publishing your results, and that sample that you are working on for that specific paper would be preferably later on available with a common format. As an example, we can give for Jacek et al. Paper when after they work, they put it in Sinbad, the data, so later on if somebody wants to use this data as a calibration for their own software, it's fully available without any problems. And they are using actually FITS format, which is quite common in astronomy. And our suggestion, if we are deciding to use the FITS, we should also have a header informing about the observer, about the station, about the camera that was used, also which corrections we were applying. So whoever is going to use our data is already aware of already applied methods before the final data we access it. I mean, we know what was before we got the data. And the basic data that this file could include is just wavelengths and then instrumental or relative intensity, calibrated intensity, and then calibration curve itself. So we can always recreate data in both directions. We didn't spend too much time at modeling, but we at least could present where we are with some of the moments in our works. So one of the examples where we can already have some play with modeling, or our initial modeling, is one of the online available tool, which link we will be also giving in our paper. So it's a physics software that we just need to define lines that we want to have it, and on this basis we can play with the broadening, instrument broadening, and start to fit the data to those profiles. It's not strictly modeling, but at least it gives us already information about our system, about some features that we might not have taken into account. Perhaps soon, I hope, it's the part of the ESA research group that also we are working about having open source software that includes also the spectra part. It's still under construction, but we already have a cooperation with Stuttgart University who can provide us the modeling corner that we can feed our software. This actually is an example of the table that is in that IMO handbook. So there was a question also during the workshop, so which lines we should take into account, which not because they are less common in spectra. That document, it's again a good starting point to look at. and gradually add it to your own databases. Results from EG paper from 2005 and follow years, also Peter Jennison's paper, where is also a huge table of the elements that were observed in the set of spectra. And we had also quite nice part where we were taught how we should properly prepare the ternary graphs and actually how we should properly also interpret the results together with the information from velocity measurements. So it's not just ternary graph and what is there, but also look how the velocities are going to tangle all of these informations. And I will finish here. Yeah.
Thank you, Regina. Any questions or comments?
I have just comment that to enhance the scientific value of the spectroscopic data, it is advisable to have full information about the meteor. That means the velocity, height, orbit. So it's better to have not only spectroscopy but triangulation connected with the spectroscopy.
Anyone else? You can put a grating in front of a camera, but do you think that if you've not done this before, there is a big learning curve before you can get science compared to some branches of meteor astronomy?
I look at the video spectroscopy as a complementary work for the dynamic or trajectory calculations, because we are tackling from both sides. It's not just something later for Jeremy to do the modeling, but also when he points a comet or an asteroid, we already have an idea what maybe type of material that object is. So it's not like pinpointing that it's that asteroid or that comet, but it gives a feature of the material itself. So it's always a good complement. And besides, if somebody wants to study astronomy in general, like through the trajectory calculations and all the calculations, we are learning mathematics or geometry, trigonometry, and this is the starting point for whoever wants to be interested in general in astrophysics.
Yeah.
Very cheap, maybe not perfect resolution, but it's a starting point to go and graduate in the different levels of astrophysics.
Yeah. Okay, thank you, Regina.
For a second of time, I will just leave it that last page. There's a deadline for research fellows, and because I'm leaving, then the seat is free in the moment, so somebody can apply. But not only postdocs can you can apply for the postdoc position, but it's also some programs for students soon after they master, and young graduate trainees, which is also after the master. So the first one could be like 3, maybe 6 months project. Where with the second one, it's a year full project with already existing missions in ESA. So you can apply, and in context of the research fellow, the deadline is 1st October, so please hurry because you need to contact somebody locally, you need to have an official supervisor. Yeah, thank you.
Thank you.